In this video, we're going to be discussing states of matter, their properties, and changes between those states of matter. The three states of matter we're going to consider will be solids, liquids, and gases. And shown here are the 6 different phase changes which we'll discuss. Those phase changes between solids and liquids, liquids and gases and solids. First, to look at some different properties of these 3 phases of matter. These should be familiar to you, but it's probably good to review. Starting with solids. Solids tend to have ordered arrangements, particles essentially in fixed positions, and the particles very close together. You know that's what gives solids their hardness and their definite shape. If you heat a solid, you can turn it into a liquid, where there's more disorder. Particles are free to move relative to each other, but those particles are still close together. Then, if you heat a liquid, or reduce a pressure, which is something we'll look at a little bit later, you can turn that liquid into a gas. Gases have total disorder, there's lots of empty space, the particles have complete freedom of motion, and are very far apart. In essence, what we've done here is broken all the IMFs between the liquid. Moving from a solid to a liquid, you notice that it goes from being incredibly ordered to somewhat ordered, or some disorder in the liquid. There we're only breaking some IMFs. So what we're going to be looking at in this video is whether energy is needed to break IMFs, or if energy is released in forming IMFs. Moving from a gas to a liquid releases energy as IMFs form. And moving from a liquid to a solid again releases some energy as IMFs form. Focusing first on liquids, there's 2 properties of liquids that I'd like to look at. The first is surface tension, which is the tendency of a liquid to minimize its surface area. Where we see this is with a ball of water balling up or beating up as small as it can into a droplet. Something like this, which you might notice. Other liquids that have less surface tension might bead less or might spread out entirely. This surface tension is due to the IMFs of the molecule. Another property of liquids that we see is viscosity. Viscosity is the ease with which molecules can flow past each other. And we talk about things that have high viscosity or are very viscous, such as maybe maple syrup, or things that have low viscosity or are not very viscous. And that would be water as an example. There again, we're talking about the intermolecular forces between those compounds. Another good question to ask ourselves is, can all 3 phases of matter exist at once? In this image, I think we have a nice example that says absolutely yes. You have solid icebergs, liquid water in the form of the ocean water, and then water vapor in the form of the vapor in the clouds, or vapor in the atmosphere above the water. For the second half of this video, let's focus on changes between the states of matter. Looking on the left, you see the enthalpy, or the energy, of the system. Notice that solids have the least energy, liquids a little bit more, gases a little bit more, and then if you were to ionize a gas and turn it into a plasma would have the most. Keep this graph in mind, as it will help us remind ourselves whether energy is needed or energy is released in these different phase changes. Evaporation is our first phase change, going from a liquid to a gas. This process, as you can see from the graph, requires energy, or we can think about it conceptually, because we're breaking IMFs, it requires energy. 2 terms to keep in mind here. The boiling point, or the normal boiling point, is the temp at which a liquid boils at 1 atmosphere of pressure. And it turns out that the boiling point depends on the pressure pushing down on that liquid, which is something that we'll look at a little bit later. At higher altitude, where there's less atmospheric pressure, liquids actually boil at lower temperatures. This is one of the reasons that a pressure cooker might be needed to bring boiling water temperatures up to higher temperatures. This is related to the idea of vapor pressure. Vapor pressure is the pressure of the gas phase of a substance as it is in equilibrium with the liquid. Here we're introducing a term we haven't seen yet, equilibrium. Equilibrium deals with the rate at which things happen. So a vapor pressure is defined that when the rate of evaporation is the same as the rate of condensation, there's a certain pressure of the vapor phase or of the gas phase of that substance. The best way to think about this is with a cup of water. Leave a cup of water out in a room and some of the particles will begin to evaporate away. However, the atmosphere also has some water vapor in it which will condense in that cup of water. When the rate of evaporation equals the rate of condensation, whatever the concentration of the water vapor in the air is at that point, that's the vapor pressure. This will be more important to us later when we talk about gases. I've now mentioned condensation. That's just the reverse process of a gas going to a liquid. And notice that releases some energy. There's a couple of pictures that might aid us here. At a given temperature, a temperature is simply an average of the average kinetic energy of all the particles in a system. So at a lower temperature, you see that some particles have higher energy and some have less energy, and some will have enough energy to begin to boil. At a higher temperature, the percentage of those molecules that have enough energy to boil goes up. Not all of them do, which is why things don't boil instantaneously, but many of them do, which is why they might boil faster at a higher temperature. Here we get a nice visual of evaporation. As those liquid water molecules gain enough energy to overcome their IMFs, they can separate from each other and enter the gas phase. And here we see a nice graphic of that equilibrium between liquid water and gaseous water in this third graphic here. Once they reach an equilibrium, the pressure exerted by these gas molecules in the vapor phase, that gives us our vapor pressure. The next two phase changes are melting. Melting is the phase change from a solid to a liquid. As you can see, it requires some energy. The melting point is simply the temp at which melting occurs. For some substances, such as water, this happens at 0 degrees Celsius. And for some substances, such as gallium, the melting point is low enough and your hand is actually sufficient in supplying energy to cause melting. Freezing is the reverse process, liquid into a solid, that releases some energy. This is maybe a little bit foreign to us as we typically think of requiring a freezer to cause liquid water to become solid water, but really what that freezer is doing is removing energy from the system to cause it to freeze. Deposition is a little bit of a rarer phase change. This is a substance moving from a gas to a solid. As you can see, this releases energy. This maybe most commonly happens on a cold day when your car windshield collects water vapor in the form of frost. And that's a transition directly from gaseous water vapor to solid ice on your windshield. Finally, we have the phase change sublimation, moving directly from a solid to a gas. Not all substances sublime. It requires a particular combination of temperature and pressure. But one good example is carbon dioxide. And carbon dioxide in the form of solid, dry ice will sublime directly into gaseous carbon dioxide. The only way to force CO2 into a liquid phase first and then into a gas is to dramatically increase the pressure, which we don't encounter under most normal circumstances. So again, as a review, we have 6 different phase changes: evaporation, condensation, melting and freezing, deposition, and sublimation. Keep in mind whether energy is required or released during those phase changes. Thanks for watching.